Hello everyone, my name is Akila Hanis binti Abdulaziz. Today we are going to discuss an important infrastructure project which is penggantian Jambatan Sungai Rincing in Hulu Langat, Selangor. This project showcases the use of pre-stressed concrete, known for its strength and durability. Let's begin by understanding pre-stressed concrete. This method involves applying internal stress to counteract external loads, which greatly enhance the structural strength and longevity of the material. It's particularly effective for large-scale projects such as bridge, high-rise buildings, and flyovers, especially those exposed to significant tensile stresses. There are two methods of pre-stressing. First of all, pre-tensioning. The steel tendons are stretched between external buttresses before pouring the concrete. Next, post-tensioning. In this method, steel tendons are tensioned after the concrete has solidified. Both approaches ensure improved performance and resilience of the structure. Why use pre-stressed concrete for the Sungai Rincing Bridge? The material provides several advantages, such as it allows for longer span without needing excessive structural depth, and it also reduces the dead load while maintaining strength, enhancing overall efficiency. By minimizing cracks, it increases durability and protects the steel reinforcement from corrosion, thus ensuring the bridge longevity and sustainability. In conclusion, the implementation of pre-stressed concrete for the Sungai Rincing Bridge project not only addresses the structural demand but also extends its lifespan without contributing to sustainable development.
My name is Anis Izzati binti Shukri and my metric number is 2024X02096. So next, I will continue to the type of pre-stressed concrete. There are two main types of pre-stressed concrete, which are pre-tension concrete and post-tension concrete. Pre-tension concrete involves tensioning the tendons before pouring the concrete. This method is typically done in a factory setting, making it ideal for precast elements such as beams, slab, and bridge component. In pre-tension, the tendons are stretched between strong and encouraged, and once the concrete hardens, the tension is released. The bonding method is tendons are bonded to the concrete directly, providing immediate pre-compression. Pre-tensioning is efficient in producing high-quality, consistent products due to controlled factory conditions. The cost of pre-tension concrete is lower on-site cost, but it can lead to higher transportation costs since the elements are prefabricated off-site. On the other hand, post-tensioning concrete involves tensioning the tendons after the concrete has been cast and cured. Unlike pre-tensioning, this method is often done on-site, making it suitable for large-scale structures like bridges, shell roof, reservoir, and flyover. In post-tensioning, ducts or sleeves are placed in the formwork before pouring the concrete. Once the concrete cures, tendons are tensioned and anchored, creating the compression within the structure. The bonding method is tendon can be bonded via growth or unbonded, allowing free movement within ducts. Post-tensioning provides greater flexibility for a complex and large-scale project. The cost of post-tensioning concrete is higher on-site construction costs due to the need for specialized equipment and skilled labor. After that, the major components of pre-stressed concrete. First, it involves tendon. It is made from high tensile steel wire, strands, or bar with a diameter ranging from 2 to 7 mm. The tendons provide the internal pre-compression that enhance the concrete strength, allowing it to withstand higher load and longer span. Second, concrete. It must have high compressive strength, with grade 40 for pre-tension application and grade 30 for post-tension application. The concrete is composed of Portland cement, fine or coarse aggregates, admixture, and water. Third is anchorage system. This system is essential for attaching the tendons to the concrete member. It includes load distribution devices like split convergers and pressure plates. The anchorage system is critical for effective transfer of pre-stressing force into the concrete. fourth is reinforcement. Actional reinforcement is added near anchorage point to handle shear forces and local stresses. This reinforcement can take different forms such as helical reinforcement added at anchorage position that handle local stresses, while traverse reinforcement across the member improves structural integrity. Fifth, formwork used to shape and support the concrete during casting. Formwork must be precise, especially for pre-tensioning and post-tensioning methods. In pre-tensioning, tendons are tensioned before the casting of concrete, a method frequently employed in precast components. In post-tensioning, tendons are tensioned subsequent to curing, providing adaptability for cast-in-place application, particularly for longer spans.
Next part is about the construction process for prestressed concrete structure. First, design and planning. The first stage of build a prestressed concrete structure is design and planning. It is to consider technical, analytical, and practical factors to ensure efficiency, safety, and compliance. Second, preparation of mold and reinforcement. This process includes a step to ensure that the formwork and reinforcement meet the specific requirement for prestressing. Concrete is poured into a mold that acts as a temporary mold until time when the concrete has hardened and become strong. Third, placement of tendons. Tendon placement is important for structure integrity and stress distribution in prestressed concrete structure. For post-tensioning, install the channel or sheath in the mold and align the tendons properly. For pre-tensioning, making the tension tendons with hydraulic jack when the concrete has gained sufficient strength. And for next step is concrete placement. In this phase, concrete is poured mechanically with a pump manually or with a bucket, depend on the size and complexity of the structure. The concrete is poured in layers no more than 300 until 500 mm thick for best compaction and layer bonding. Furthermore, thermal tubes, pipes, or tubes are used to control flow, prevent material separation. Next step is pre-stressing. After curing, the strained tendons are gradually released, transferring their stored elastic energy to the surrounding concrete. This transition marks the active involvement of the concrete in carrying out loads. The part comprehensive force enhances the concrete's tensile strength under extended loads. Once sufficient strength is achieved, tendons are tensioned using hydraulic jack and anchor at the end to maintain the applied compressive force. Next step is grouting. To prevent tendon corrosion, the channel filled with grout, ensuring a secure bond with the concrete. Grout is mixed using a higher speed mixer for consistency and pumped into the canal starting from the lowest inlet to allow upward flow and air displacement. Vents are closed sequentially as grout falls out, and the process is monitored to prevent void or obstruction. After filling, the grout is slightly compressed for a few minutes to eliminate gaps and avoid settlement of shrinkage. Next, we must make a finishing and quality control. In this step, apply finishing treatment for aesthetic and durability. Next, conducting non-destructive tests (NDT) such as UPV, ground penetrating radar, rebound hammer to evaluate strength, homogeneity and defect. For NDT tests, we must prepare test surface and selecting location based on design or area of concern. Furthermore, use calibrated equipment for NDT and interpreting results with charts or software tools, also making the document test result. And last part is maintenance. For prestressed concrete structure to perform effectively, safely and reliably over their design life, maintenance forms one stage of their life cycle. This phase starts when construction of the concrete structure has been complete.
Assalamualaikum, my name is Atira Fatnin. I will proceed with material and equipment use. The first material used is concrete. Concrete has high compressive strength, making it ideal for supporting heavy loads during the pre-stressing process, and it can withstand various environmental conditions. For pre-tension concrete, the minimum grade is 40, while for post-tension concrete is 30. allowing for greater load capacity and longer span compared to ordinary reinforced concrete. The next one is high-strength steel. High-strength steel tendons with a typical yield strength of around 1860 MPa are designed to withstand heavy load and tensile forces in pre-stressing application. This steel is ductile, allowing for deformation without damage, and has corrosion resistance, ensuring a longer lifespan for structure. Next is cement. Portland cement is the primary binding agent in concrete, reacting with water to form calcium silicate hydrate, which provides strength and durability. High-performance Portland cement is used for pre-stressed concrete to achieve the necessary compressive strength and durability, making its quality crucial for overall concrete performance. The last material is aggregate. Aggregate make up 60% to 80% concrete volume and are divided into coarse and fine aggregate, essential for the stability and strength of the mixture. Quality aggregate should be clean and free from contaminants to ensure a strong bond between the cement paste and the aggregate. For the equipment, the first one is hydraulic jack. Hydraulic jack are used to tension tendon and apply control stress to them before the concrete hardens, enhancing the strength and durability of the concrete. In pre-stressed concrete, high-strength steel tendons are tensioned inside ducts using hydraulic jack, making them essential for both pre-tension and post-tension method. The next one is concrete mixer. Concrete mixer are essential for achieving a consistent and strong concrete mix by thoroughly combining cement, water, sand, and aggregate. Proper mixing ensures the quality, strength, and durability of the concrete, contributing to the longevity of the structure. Next is grouting pump. Grouting pump inject grout into the ducts around the tension tendon, bonding them to the concrete and preventing corrosion. Proper grout injection is crucial for the long-term performance of pre-stressed concrete. Incorrect injection can lead to insufficient strength and increased corrosion risk for the tendons. The last equipment used is curing equipment. Curing equipment ensure freshly poured concrete receive the necessary moisture for the curing process, using methods like water spraying, wet cloths, and protective chemical. Proper curing is essential for achieving the strength and durability of concrete, and in cold weather, heaters may be used to maintain the appropriate temperature.
My name is Nur Ilmi. Now, I'll walk you through the standard procedures we follow in our work to ensure both quality and safety. We adhere to two key standards, which is British Standard Institution BSI guidelines, particularly BSEN 2006-1:2000 ratio, which governs concrete strength, CIDP Malaysia guidelines, which complement the BSI standards with region-specific requirements. Let's talk about the two main considerations. Firstly is the strength. We comply with BSI standards, ensuring that all calculations and drawings reflect the required design strength. Before demolding or detensioning, cube strength testing is conducted to validate compliance with the design strength. Second is design consideration for lifting. Proper marking of lifting points is critical to ensure safe handling. Various lifting methods such as chains, clamps, and hooks are carefully selected based on the requirements. By following these standards, we ensure structural integrity and safe handling processes. Moving on to the manufacturing process, we focus on 4 key steps. First is tendons. These are critical for pre-tensioning. Pre-tensioning a vital step that ensures the structural capacity of the component. Stressing limits. We ensure all tendons are stressed within permissible limits to avoid failure. Slippage and realization. Monitoring is done to minimize losses in tendon strength over time. Next is the process of detensioning, which has its own set of strict guidelines. When to start, detensioning begins only after compressive cube strength has been verified. The minimum waiting period is 18 hours unless expedited curing is approved. How it's done? Tendons are carefully cut using abrasive wheels or flame cutting with strict adherence to safety margins. By adhering to these steps, we ensure that the components meet the required quality and performance standards while maintaining safety throughout the process.
Next, we have one case study for this assignment. We refer for our topic pre-stressed concrete structure. We get the project from JKR. Name of the project is Penggantian Jambatan Sungai Rincing, daerah Hulu Langat, Selangor. And project location at Hulu Langat, Selangor. For project duration is 783 days. And the completion date is 15 December 2025. For structure component used in this project is pre-stressed concrete beam, reinforced concrete beam, slab, diagram, curb, parapet, board piles, and box girder. And the types of tensioning used for this project is pre-stressed post-tensioning T-beam, semi-integrated abutment.
Now, let's move on to the parties involved in the construction process of pre-stressed concrete structure. In any construction project, multiple key stakeholders play a critical role to ensure the project is executed successfully. For the Sungai Rincing Bridge project, the main party involved are the client, which is Kementerian Kerja Raya Malaysia. The project manager was handled by Adat 88 Sdn Bhd, the superintendent officer, which is JKR Hulu Langat, the contractor, which is Adat 88 Sdn Bhd. Design team. The design team was led by Jabatan Kerja Raya Wilayah Persekitaran Kuala Lumpur, which include the architect from the bahagian architect, the quantity supplier from bahagian kontrak dan ukur bahan, the civil and structural engineer from bahagian reka bentuk awam dan struktur, the mechanical engineer from bahagian mechanical, the electrical engineer from bahagian electric. These parties work together to ensure that the bridge met all design safety and regulatory requirements, resulting in a durable and efficient infrastructure project.
The next one, I will discuss about the construction process. The first step in bridge construction is design and planning. In this step, we need to consider factors such as the expected loads, spent materials, and the structure's ability to withstand stress and strains over its lifespan. Then, site preparation. After finalizing the design, site preparation involves removing obstacles, leveling the ground, and assessing soil bearing capacity to ensure the foundation can support the bridge weight. Then is the formwork installation. Formwork shape concrete during curing and must be carefully handled to support weight concrete weight, be waterproof to prevent leakage, and install precisely to maintain the bridge structural integrity. Next is reinforcement placement. Steel reinforcement bar must be placed according to design specification to provide the necessary tensile strength for the bridge, as concrete is strong in compression but weak in tension, and precise placement is crucial for effective integration. After that is duct installation. Duct must be precisely placed for the post-tensioning process, allowing for uniform application of compressive forces to the concrete. The next step is pouring the concrete. Concrete must be of high quality and properly mixed, and vibration technique should be used during pouring to eliminate air pockets and ensure it fully envelopes the reinforcement. Then, it is continued with curing process. Curing maintains moisture and temperature for concrete to gain strength, preventing cracking and ensuring it reaches its full potential, typically lasting several days. Next, once the concrete has sufficiently cured, the tendons are tensioned using hydraulic jets. We compress the concrete and enhance the structure's load-bearing capacity while preventing cracking under stress. After tensioning, the tendons ends are securely anchored to the concrete to effectively transfer force and ensure the bridge remains stable and safe. After that, grout is injected into the duct after tensioning to protect against corrosion and bond the tendons to the concrete. We careful monitoring to avoid voids that could compromise structural integrity. The last step is finishing touch. After tensioning and grouting are complete, the formwork is removed and finishing work is done, including smoothing the surface and installing features like railing and lighting to enhance the bridge usability and safety. For the safety procedure, the first one is emergency response preparedness. Emergency response preparedness is crucial for construction project involving training personnel on emergency procedure, conducting drills, and ensuring response teams are equipped with clear evacuation routes and communication protocol for a rapid response. Next is hazard management. It involves identifying potential risk in construction and implementing strategy to mitigate them, including engineering control, administrative control, and personal protective measures to reduce accident and injuries on the job site. So the next one is PPE. PPE is essential for workplace safety, mandating the use of gear like hard hat, safety goggles, glove, hearing conservation device, and life jacket to minimize injury risk and promote a culture of safety. The last safety procedure is regular inspection. Regular inspections are crucial for maintaining a safe work environment by identifying hazards, ensuring equipment is safe, and verifying compliance with safety protocol like PPE used to prevent serious incidents.
Next, we will discuss the key challenges associated with the project and the solution designed to address them. These challenges are typical in large-scale infrastructure projects but can effectively managed with proper planning and execution. One major challenge is traffic disruption. Construction activity often hinder existing routes, causing delays for commuters and businesses. To address this, phased construction will ensure portion of the road remain open during the project. Second, we will implement a comprehensive traffic management plan with clear signage to guide commuters. Lastly, alternate routes will be used, and we will conduct nighttime or off-peak construction to minimize the impact on daily traffic. Another significant challenges involve relocating utilities such as water pipes, electrical cables, and communication lines that may cross the construction site. To manage this, we will use advanced technologies like ground penetrating radar, GPR or GIS to map and locate the utilities accurately. Next, coordination with utility provider will align relocation effort with project timelines. Lastly, trenchless technologies like horizontal directional drilling will be employed to minimize disruption during utility relocation. Furthermore, there is the challenge of project delay, often caused by unforeseen factors such as bad weather, soil condition, or resource constraint. Our solution include firstly, developing realistic schedule with contingency plan and address setback. Next, using precast bridge segment to reduce on-site work and mitigate delays. And lastly, employing pre-assembled component off-site to avoid weather-related disruption and ensure a steady supply chain. The next challenges is space limitation. In congested area, finding adequate storage and space for equipment can be significant constraint. To tackle this, prioritize compact and mobile equipment, ensuring they fit within limited space available. Next, implementing just-in-time JIT delivery for material will reduce the need for on-site storage. Lastly, if necessary, we will lease adjacent land for temporary storage or staging, enabling smooth workflow without obstructing the primary site. Last challenges is environmental disruption, including noise, air pollution, and disturbance to nearby neighborhood. To mitigate this, we will use noise dampening technology and schedule noisy activity during acceptable hours to minimize the impact on residents. Lastly, regular maintenance and monitoring will ensure minimal environmental harm while keeping the project compliant with regulation. By effectively addressing these challenges, we can not only maintain productivity but also ensure that the surrounding community and environment remain minimally impacted. This approach underscores our commitment to sustainability and operational excellence.
So this is our two comparison of our case studies. Now, let's dive into a comparative analysis of two case studies. First is Sungai Rincing Bridge in Hulu Langat District, Selangor, and Delhi Merit Project Expressway. Problems identified for the Sungai Rincing Bridge. Firstly is traffic disruption. Construction caused inconvenience to road users and relocation of utilities. Utilities in the construction area needed to be relocated, causing delays. Next is the project delays. Various factors compounded delays in the project timeline. For the Delhi Meerut Project Expressway, the site limitation will be caused for this project. The site posed physical challenges such as limited space, preparation of precast girders, and ensuring the quality and accuracy of precast girders was a concern. Next is transportation and erection issues. Discuss logistical difficulties during implementation. Solutions implemented to address the issues at Sungai Rincing Bridge is firstly for the traffic disruption. Phase construction was implemented to keep parts of the road open and minimize impact on commuters. Next is relocation of utilities. A utility mapping survey was conducted to identify affected utilities early, allowing for relocation planning. For the project delays, strategies were developed in advance to mitigate potential delays. For the Delhi Meerut Project Expressway, the site limitations, the use of initial setting admixtures accelerated the setting process, optimizing construction despite special constraints. Next is preparation of precast girders. Precast elements were utilized to maintain quality while meeting deadlines. Transportation and erection issues. The conventional pretension girders were employed as a practical solution to overcome these logistical challenges. Through this tailored solution, both projects were able to mitigate challenges effectively and progress towards successful completion. This analysis highlights the importance of proactive planning and innovative approaches in overcoming project-specific challenges.
So for the conclusion, precast concrete offers significant advantages over conventional reinforced concrete, particularly in modern construction. By introducing internal compressive stresses through methods like pretensioning and post-tensioning, precast concrete helps in effectively eliminating the tensile stresses that most of the time have led to cracking and enhancing the lifespan of structure. Based on the case study, which is the construction of the project Penggantian Jambatan Sungai Rincing daerah Hulu Langat Selangor, it can be concluded that the method of precast concrete used is the post-tension method. Post-tensioning enables bridges to meet highly demanding geometric criteria such as complicated curve, variable super elevation, and considerable grade changes. Post-tensioning allows long-span bridges to be built without temporary intermediate support, which reduces environmental impact and avoid disrupting water or road traffic below. Thus, this makes precast concrete an ideal choice for modern engineering applications, enhancing safety, durability, and aesthetic appeal while meeting today's demand for performance and sustainability. That's all from us. Thank you.